All right, exams are just around the corner, and you need the absolute key points on force and pressure, and you need them fast. Well, you are in the right place. Think of this as your high-speed, no-fluff guide to completely nailing these concepts. Okay, let's get right into it. We're going to jump straight in with a question that could be pulled right out of your textbook, because this is exactly how you need to be thinking for your exam. What happens if an unbalanced force acts on a moving object? This question gets right to the heart of what forces actually do, and believe me, by the end of this, you'll know exactly how to answer it. So here's our game plan for the next few minutes. We'll kick things off with the basics of force, then we'll see how that connects to pressure. After that, we'll hit the crucial formula you absolutely have to memorize, and finally, we'll look at some real-world examples that are just perfect for exam questions. Okay, first things first. We have to start with the absolute foundation. You really can't get the rest of this stuff until you've got the difference between balanced and unbalanced forces locked down tight. And the key difference is all right here. So on the left, you've got balanced forces. A perfect example is a book just sitting on a table. You've got gravity pulling it down and the table pushing up with the exact same force. And the result? Nothing. No change in motion. But on the right, if you give that book a push, suddenly the forces are unbalanced. And that is the number one thing you need to remember. Unbalanced forces are what cause a change in motion. They make things speed up, slow down, or change direction. So now let's move on to our next big idea, and you'll see how this all connects. It is so easy to mix up force and pressure, but trust me, they are not the same thing. And understanding that difference, well, that's the secret to getting a ton of real-world physics problems right. Check this out. This slide shows a classic experiment that just perfectly explains the idea of pressure. We've got a simple wooden block and a patch of sand. Now we're going to apply the exact same force in both scenarios, which is just the block's own weight, but you're about to see two completely different things happen, all based on how that force is spread out. And here we go. When the block is lying flat, its weight is distributed over a big wide area, so it barely even makes a dent. But when you stand that same block up on its narrow edge, the exact same force, its weight, is now concentrated on a teeny tiny area. This creates way more pressure, and the block sinks right into the sand. This relationship is absolutely everything when it comes to pressure. All right, pencils ready, because this is the part that is pure exam gold. The relationship we just saw with the block and the sand, it can be described with one simple but incredibly powerful formula. Let's break it down. If you're asked for a formal definition on your exam, this is it. Memorize it word for word. Pressure is the force acting normally, meaning at a right angle, on a unit area of a surface. It's clean, it's simple, and it will get you full marks. And here it is, the golden formula. P equals F over A. P is for pressure, F is for force, and A is for area. Now look at this formula. It shows you everything. When the area on the bottom gets smaller, the pressure on the other side has to get bigger. It's an inverse relationship, and it perfectly explains why that block sank into the sand when it was on its edge. And please don't lose easy marks over units. Force is always in newtons, which we shorten to N. Area needs to be in square meters, and that means pressure is measured in newtons per square meter. But it has a special name that you have to use, the Pascal, or PA for short. So let's see this formula in action. In this little exercise, Ollie's weight is a force of 500 newtons. The area of his shoes on the floor is 0.025 square meters. We just have to plug those numbers in, 500 divided by 0.025, and that gives us our answer, 20,000 pascals. It really is that straightforward. Okay, so you have the formula down. Now, let's use it to understand some classic examples that just love to pop up in exams. This is where you really show the examiner that you don't just know the formula, you actually understand it. Think about a drawing pen. I mean, why does the sharp end go into the board and not the flat end into your thumb? Well, the force from your thumb is the same in both cases. But that tiny sharp tip concentrates all of that force into a super small area, creating immense pressure that can easily pierce the board. A blunt pen? It has a larger area, so the pressure is much lower, and it's way harder to push in. Here is another brilliant way to remember it, and a great detail to drop in an exam answer. Even if a woman weighs less than a man, the tiny area of her stiletto heel concentrates all of her weight into one little spot. This creates way more pressure on the floor than the man's flat, broad shoe, which spreads his weight out. So, we've seen how pressure works with solid things, right?
But the same exact principle applies to gases, like the air all around us. You see, the air is made of billions and billions of tiny molecules that are constantly zipping around and colliding with every single surface. Each one of those little collisions is a tiny force. When you add up all those forces over an area, you get what we call air pressure.
And a parachute is just a perfect illustration of this. When a paratrooper opens their chute, what are they really doing? They are dramatically increasing the surface area. This giant area catches way more of those air molecules, creating a huge upward force from air pressure that fights against gravity. This upward force, or drag, slows them right down so they can land safely. It's all about using a large area to make air pressure work for you.
So, let's wrap this up and boil it all down. If you remember nothing else, burn these 4 points into your brain. 1. Unbalanced forces change an object's motion. 2. Pressure is force divided by area. 3. For the same amount of force, a smaller area means much greater pressure. And 4. The unit for pressure is the Pascal. This is your exam flashcard right here.
And we'll end where we started, with a question to get you thinking. We've talked all about force and pressure. So how can you use these concepts to explain why a massive, heavy ship made of steel can float, but a tiny little steel nail sinks instantly? It's a great puzzle to chew on for your next topic. Good luck with your revision. You've got this.